Now I kind of lost track of this, but here's the same, we're addressing the same thing. S over S squared plus pi squared over 4 is S over S squared plus omega squared. 4 omega equals pi over 2. Okay. Now this is from the table, and if you follow what we did previously, you see that immediately. So the inverse Laplace transform of this is a cosine of pi over 2 times t. And that takes care of our, so the 1 over S squared plus pi over 4 squared. Okay, well, that's it. That's it for the S over S squared plus pi squared over 4 that we had previously. Yeah, I don't think yeah, actually I can get to that. Here, let me just kind of expose that again. Okay, now hopefully you can see enough of this, and you can see where we reversed, where we broke the one expression down into this. So this is addressed here once more. Probably get tired of seeing it, but let's make sure we understand it. Then 1 over S squared plus pi squared over 4 is of the form omega over S squared plus omega squared, multiplied by some constant. And the constant is what? Well, to get this from this, the constant ought to be 1 over omega. Omega is pi over 2. Omega squared is pi squared over 4, so omega is pi over 2. So that 1 over omega is 2 over pi. So the inverse Laplace transform of this, well, it's 1 over pi over 2 times the sine of pi over 2t, 2 over pi times the sine of 2 over 2, pi over 2t. So the inverse Laplace transform of our S plus 1 over S squared plus pi squared over 4 is cosine of pi over 2t plus 2 over pi sine of pi over 2t. Now, the thing we really illustrate by breaking this down is that we've got to do a little algebra, and we've got to be a little bit creative. We've got to be able to do the algebra, we've got to be able to manipulate the algebra to get an expression like this into a combination of expressions, a sum of expressions that appear on our table, or sum of expressions for which we can derive the Laplace transforms. Okay? So we have this, and of course you can recognize this now as maybe a typical solution to a differential equation where you have a fundamental set cosine pi over 2t, sine pi over 2t. So maybe we transformed a differential equation and got this, and that differential equation might well have included initial conditions. If it didn't, there are parts of this that we probably wouldn't get. So that this is the linear combination of our fundamental set that satisfies that equation with those initial conditions. So next thing we want to see is how do you transform a differential equation, and where does that lead you?